Okay, so welcome back to the SEED seminar. We are starting a bimester in geometry and general relativity. It is my pleasure to introduce Bram Petri today. Bram had his PhD in the University of Fribourg and is currently a maître de conférence in Sorbonne Université. He will talk about linear programming on hyperbolic surfaces. Please, Bram. Please go ahead.
Right. All right. Thank you very much for having me in the seminar. So yes, I'm going to talk about linear programming on hyperbolic surfaces. Everything I'll say is joint work with Maxime Fortier Bourque from the University of Montreal. And so this is definitely a talk on in the geometry side of things. There are connections to physics, but I am not qualified to talk about them, so I'll just talk about the geometry. Also, since I know it's a seminar for a large audience, please don't hesitate to interrupt if I use terminology that you're not familiar with, or any question at all. So yes, so our work with Maxime is in a sense a hyperbolic analog of classical packing problems in Euclidean space. So to motivate it a bit, I wanted to start with packing problems in Euclidean space. In particular, I wanted to tell you about a theorem by Kohn and Elkies, which gives an upper bound for the density of a sphere packing, which inspires a lot of our work. So I'm going to start with that. And then I'll explain something about the geometry of hyperbolic surfaces and the type of problem Max and I are working on. All right. So first of all, the Euclidean case. So on the screen, you see a picture of a packing. It's a lattice packing. And so it's a collection of disks with disjoint interiors in the plane, and there are multiple extremal problems you can pose for these types of packings, or basically two. The most studied problems are the density and the kissing number. So the density of the packing, I'll put down a formal definition in a minute, but it's the proportion of space that is filled up by the disks, and the kissing number is the number of disks that are tangent any given disk. So in this case, this is a packing with kissing number 6, because if I take any disk in the packing, it touches it's tangent to 6 other disks. And even in the Euclidean case, there are many open problems. So I just recorded, for some context, I recorded some facts about kissing numbers. So first of all, if you restrict to lattices, so packing doesn't have to be a lattice, but if you restrict to lattices, meaning the centers of the spheres form a lattice. So so lattice here is just you take a basis for Rn, and you take all integral linear combinations of the basis. This is a lattice. And even then, if you want to maximize the kissing number, so you fix the dimension and you ask how many spheres can I make kiss a given sphere. So in dimension 1, this is a very simple problem. In dimension 2, you see the realizer on the screen. This is the one with maximal kissing number. This is also an exercise. It's an exercise in Euclidean geometry. In dimension 3, it's already harder. So the maximizers are known only in dimensions 1 up to 9 among lattices, and dimension 24, even for this, even in the Euclidean case. Then you can also ask, just to give you some numbers. So the 24-dimensional one is the Leech lattice, which always pops up in these kind of extremal problems. In dimension, the Leech lattice, it doesn't matter so much what the definition is at the moment, but it's a lattice in 24-dimensional Euclidean space, and it maximizes pretty much every extremal problem you can think of. And for the kissing number, it has a kissing number almost 200,000. So there's about 200,000 spheres that are tangent to any given sphere in this packing. So that's quite enormous, and that's not a coincidence, because it's also what is also known is that the maximum grows exponentially with dimension. Even this is pretty recent. So the upper bound is from the 70s due to Kapodiansky-Levenstein, but the lower bound, so creating examples of lattices with exponential kissing number, is only 3-4 years old due to Vladut. All right, so that's the kissing number problem in Euclidean geometry. And then the problem that I really want to talk about in Euclidean geometry is the density problem. So this is here's the definition of density. Again, if P, curly P here is a packing, so it's some collection of balls in Rn with disjoint interiors. And the density delta P is just the proportion of space that is filled up by your balls. So what do? You take a ball of radius r at the origin, you count how many centers are contained in this ball, and you compare that to the volume of the ball. And sorry, I should have yeah, okay, I should have added the volume here. This plays the role of the density. Okay.
Sorry, P is the lattice. P is
the lattice. P is the collection of centers. Yeah, I mean, it doesn't have to be a lattice in sphere packing, but the case that interests me actually is lattices.
And in the first picture, you said that it's maximizing. It's about the angle between the two generator of the lattice that is maximizing. I mean, it's associated to the angle.
It's associated to the angle. Yes, that is exactly, that is the crucial observation here. Is that you get if you get this is how you prove that this one is maximal in dimension 2. Actually, like you look at the, let me draw. So you look at this angle, and then you realize if all three balls here are radius 1, then you have a lower bound on this angle, and it's realized by this packing. This is the
Thank you very much.
Exactly. All right. So the density problem is what, if I fix the dimension, how large can this number be? That is the density problem. And I want to talk about. Sorry. There's the problem. I want to talk about this for a little bit. And the first thing I wanted to say is that actually knowing the density is the same as knowing the shortest lattice vector. Meaning I can equivalently ask, if I fix the volume, how large can this fix the volume of a fundamental domain for the lattice? How large can the shortest lattice vector be? That is equivalent to knowing the density, because you can, given the shortest lattice vector, you know which radius of balls fit around your lattice, and then you can calculate which proportion of volume is taken up. So this is that's the same thing, and I'm going to phrase everything in terms of shortest lattice vector, because in the hyperbolic analog to this, that is more natural. But it's really equivalent to knowing the density, which is how it's usually phrased. Okay, so I want to tell you about the upper bound that Cohn and Elkies gave on this problem. To start, for that I need the Poisson summation formula. So the Poisson summation formula is a formula that has a priori nothing to do with packings, except that lattices appear in it. So what does the Poisson summation formula say? It says that if I take a function and I sum that over the vectors in a lattice, that is up to a multiplicative factor, the same as summing its Fourier transform over the dual lattice. So the dual lattice here is this thing here. This is the set of vectors in Rn that have integral inner product with all vectors in my lattice. This is also a lattice, whence the name dual lattice. Here's my convention for the Fourier transform. So you integrate an exponential against your function. So the Poisson summation formula is this last displayed formula here. So this holds for all. So I didn't want to talk about admissibility. This, of course, you need some. I mean, you already need some conditions on your function for this sum to even converge. So there are some admissibility conditions, but I'm not going to talk about that. What I did want to do, just so that this doesn't look like some random formula, I wanted to sketch where this comes from, the Poisson summation formula. So again, the statement is, if I sum a function over the lattice, then summing that's the same as summing its Fourier transform over the dual lattice. So I wanted to sketch where that comes from, because it will also inform the hyperbolic geometry case later. So I'm just going to do the case. All the difficulty is there already. I'm just going to do the case where my lattice is Z in R. Sorry, I'm going to take is Z in R. Okay, so the one-dimensional case. Then the observation is that the dual lattice is also Z. All the things that are the integral, if you multiply them with any integers, that is the set of integers. So dual lattice is also Z. Lattice also Z, and the co-volume is 1. It's the volume of the circle, R1Z, which is 1. Okay, so I just want what the Poisson summation formula says in this case is that if I sum a function over the integers, that is the same as summing its Fourier transform over the integers. That is the Poisson. That is what I want to prove. And how do you do this? So I take my function and I define a new one, fx. This is the definition. Take my function, and what I do, I just sum my function over the whole lattice. So in this case, this is just over the integers. F little x plus a. So really, I'm really thinking of this as Z is a group acting on R by translations, and I apply the translation and I average out. And the idea is just, well, I can develop this. What do I know? I know that what's the upshot of this averaging? The silly observation is now that big F is a function that's invariant under the group action. So I have Z acting on R, and big F is invariant under Z. If I add an integer to the input, that doesn't change the function. It's invariant under Z. But that's good. That means that it's basically a function on the quotient. It's a function on the circle. On R mod Z, and that's good because that means I can write it as a Fourier series. I mean, I'm going to say, saying this in a somewhat roundabout way, but again, that has something to do with what I want to do for hyperbolic surfaces later. What I'm really doing here is I'm looking at L2 of the circle, and then I have the Laplacian acting on this thing, just the usual Euclidean Laplacian, ddx squared. And there's a spectral theorem for this operator, meaning L2 decomposes into eigenfunctions for my Laplacian. So what does the Fourier transform do? It writes my function as a sum of eigenfunctions. Okay, this is all sort of, in this case, this is all just language for saying I can write fx equals some k and z of some coefficient that I a priori don't know, times an eigenfunction for my Laplacian, or just an exponential. That is, I can write this out. And now, admissibility plays a role here, but I'm going to ignore all convergence issues in this proof sketch. And these coefficients, you can pick them out by integrating against one of the eigenfunctions, because the eigenfunctions, they're not just a basis, they're an orthonormal basis. So ck is given by the integral of fk of fx e to the power, doesn't fit, 2 pi I, sorry. Fx e to the power minus 2 pi I kx dx. All right, that gives me these coefficients. And what do I get? I get that ck, in fact, sorry, I wrote infinity and I should have written 1. Sorry, I just need to integrate over the circle, right? Oops. Okay, so these coefficients are given by the integral over the circle of the exponential times my function fx. But that is nothing else than, that is the same thing as integral from 0 to 1. Now I use just the definition of my function. N in z, f little x, little f x plus n, and then this exponential, e to the power minus 2 pi I kx dx. All right. And so what do I observe now? Now comes the trick. I flip the sum and the integral, and what I'm just integrating between 0 and 1, and then all the translates over z. So that's the same thing as just integrating over r. So this is the same as the integral over r of f hat. Not of f hat, of f x e to the power 2 pi k I x dx. But that is the Fourier transform of f, right? Evaluated at k. So this is f hat. This is little f hat of k. So this equality here, this equality, so this sum here is equal to this thing. It's f, they're both big f of x. And the ck's are nothing else than the Fourier transform of f evaluated at k. I get the Poisson summation formula. If I put in x equal to 0, then all these exponentials disappear. And then here I get the sum over z of f, and here I get the sum over z of f hat. Okay. So this little trick here. So this, I mean, modulo convergence issues disproves the Poisson summation formula. And this is what we're going to see in, I mean, I'm not going to do the proof in the hyperbolic case, but this works in hyperbolic geometry too. So so again, what is the sort of the abstract thing is I have a group acting on a space. Here it's just z acting on r. I average my function out over the group action. That means that it becomes a function on the quotient, and I use the spectral theorem of the Laplacian to develop it, to write it out. And then I get this identity. This is the sketch of proof of many trace formulas. And also just wanted to do this so that the Poisson summation formula doesn't become some sort of random formula, but the goal is just to use this formula now. So what does this give you for lattices? It gives you the following theorem due to Cohn-Elkes. So this is a consequence of the Poisson summation formula, but you don't see it in the theorem. So Cohn-Elkes, again, they're interested in either bounding the density or bounding the shortest lattice vector. And I mean, at first sight, it looks a bit like a technical theorem, but it's a very powerful theorem. So it says if you take any function, that is, I mean, it needs to be admissible and has these conditions here. I'll comment in a second, but they're just a list of sign conditions. I want it to be positive in that interval, negative in the other, etc., etc. Just a bunch of sign conditions. Then, conclusion of the theorem: the shortest lattice vector of any lattice in Rn is at most this R, which appears in the conditions. So what is this? So we have this geometry problem on finding the lattice with the largest shortest lattice vector, and this theorem turns it into a calculus problem. This now just asks for the existence of a function. All the conditions are just inequalities for the function. So I'm just asking, is there a function with this, this, and that property? And if yes, then I get a bound on the shortest lattice vector of a lattice in R. That's the upshot. The upshot is that sort of this theorem gets rid of all the geometry and just asks for the existence of a certain function. And the conditions are just the conditions are just positivity and negativity conditions on the Fourier transform. So let me just write it out, because the proof is one line now that we have the Poisson summation formula. So suppose I have a lattice whose shortest lattice vector is more than R. Suppose lambda in Rn is a lattice with shortest lattice vector of length more than R. What does the Poisson summation formula tell me in that case? And I have my function f here. The Poisson summation formula then tells me that if I look at f of 0, this appears in this sum over my lattice. This is certainly more than sum v in lambda f of v. Just because so my lattice contains 0, so it's a term on the right. And on the other hand, for all the other vectors, they have length more than R, so f is negative there. So that's the only thing I'm using here. Okay, but by the Poisson summation formula, this is the same as summing f hat over the dual lattice. Okay, just that's the Poisson summation formula. And now I'm using my second condition on f. I'm assuming that this is positive. So whatever the sum is, it's definitely more than f hat of 0, because also the dual lattice is a lattice, so it contains 0. So there's certainly the 0 term. Okay, and then I have my third condition that says that actually f0 is less than f hat. So that's definitely a contradiction, because I just derived it as more. Okay, so this lattice cannot possibly exist. If this function exists, this lattice does not. So that is the general strategy for these things. And this is called so this theorem is called a linear programming bound, because it's a set of linear conditions on a function. So and in particular, if two functions satisfy this, then a positive combinations of these functions satisfy too. So a priori, it's a linear programming problem, except that the problem runs over the optimization problem. I mean, now you want to optimize, of course, to get the best R out. But the optimization problem runs over an infinite dimensional space, which obviously causes trouble, because that means that the usual linear programming techniques, whatever they are not really going to help. All right, but just to give you an idea, what this is useful for. So here's a list of examples of things what this is used in. So first of all, in 2014, it was proved that the Leech lattice, the same thing that optimizes the Kissing number, optimizes the density problem as well among lattices of dimension 24. That's a paper by Cohn and Kumar. And then actually this theorem, so I'm mostly interested, because of the analogy with hyperbolic geometry, I'm mostly interested in lattices. But you can ask the same things for all packings, and this theorem works for all packings actually. And it was used to prove that E8, the E8 lattice, a certain 8-dimensional lattice in R8, and the Leech lattice are optimal actually among all packings by respectively Vyazovska and Cohn, Kumar, Miller, Radchenko, and Vyazovska. So when you think of this, when you think of how simple this proof is, and also if you look again, at this proof, what I'm doing here is in both these two inequalities, I'm throwing infinitely many terms away. I'm ignoring infinitely many terms. So the fact that you can, I mean, a priori, the fact that anything useful can come out of this bound might be a bit surprising, but it's not just that anything useful can come out, but you actually, I mean, you can optimize this bound, and it actually gives you the optimum in dimensions 8 and 24. So what the content is of these theorems here. Kohn and Kumar goes a bit differently, but what the content is of these theorems here is you need to find a really special function that optimizes this bound. So some complicated combination of modular forms that optimizes this bound. And that's basically the content of these two theorems. All right. Any questions so far on the on the Euclidean linear programming method? Good. If not, I was planning to pass to the hyperbolic case. So since I wrote
just a question, co-volume, it means that the volume of the fundamental domain.
Yeah, sorry. Yes, yeah, it does. Yeah.
And so this condition about the shortest vector, the length of the shortest lattice vector, it translates also to some condition on the angles between the generator in some sense. Okay, I am just, my question is there behind this, is there some condition about the angle also between the...
In this case, I'm not so sure. I'm not so sure that there's an easy way to say it in terms of angles.
Okay, that's all. Thank you very much.
Okay, if there are no other questions, then I'm going to talk about hyperbolic surfaces. So first of all, I wanted to do a quick reminder of the geometry of hyperbolic surfaces. So what are these? They're sort of so the quickest way to define what a hyperbolic surface is, even if you've never thought about hyperbolic geometry, it's not very helpful. The quickest way is to say that definition is a hyperbolic surface. Surface is a surface with a Riemannian metric. Metric of that is complete. So just as a metric space, it is complete. You don't have Cauchy sequences that don't converge, and its metric has constant sectional curvature equal to -1. So that is a definition. It's sort of a negatively curved, so Euclidean tori, which is what we've basically been talking about, the quotients of Rn by a lattice, the quotient of Rn by a lattice is an n-dimensional torus. They're constant sectional curvature 0 spaces, and this is sort of the negative curvature, I don't know, constant negative sectional curvature. An equivalent, maybe more helpful way of defining what a hyperbolic surface is that it's a surface that is locally isometric to the hyperbolic plane, locally isometric to H2. So I have to tell you what the hyperbolic plane is, but locally isometric here means that it's a surface. So I know something like this, and every point has a little neighborhood that is isometric to some region in the hyperbolic plane. That's the definition of hyperbolic surface, and it's complete. So what's the hyperbolic plane? So again, there's the quick definition, which is the unique simply connected Riemannian manifold of dimension 2 and constant sectional curvature equal to -1. But it's actually, I mean, it's something very concrete. One way to say what it is, it's the upper half plane as a set. So points in the complex plane with positive, strictly positive imaginary part, and its metric is locally just a rescaling of the Euclidean metric. So that is the hyperbolic plane. So for instance, this form with this formula, you mean that this one here. And I mean that, for instance, if you want to compute the length of a curve, gamma from 0 to 1 into H2 is a curve, what you need to do is you take the integral between 0 to 1, and then you want the length of the derivative of gamma. So this is what? You take the derivative in the x direction plus gamma 2 dot t root divided by where you are, gamma 2t dt. That is the, so this lets you like compute the length of the curve. So the fact that it says this Euclidean expression here, that comes from here, and the fact that you have this division by gamma t, that comes from this fact. So this locally gives the length of the tangent vector, the norm squared of the tangent vector. Okay, so so what does this give you? I mean, it's the upper half plane. Geodesics are so geodesics by definition. A geodesic is a path that locally minimizes length, and so geodesics are vertical lines and half circles orthogonal to R. So let me draw some circles orthogonal to R. So they've already drawn the vertical line. Here's a half circle. So what that means is that, for instance, if I want to go between here and there, the shortest route is just to go up. And if I want to go between here and there, the shortest route is to follow that unique half circle that goes through these 2 points. That's the so, and given this metric, you can compute the distance now, because you know that the shortest, you integrate over the shortest path. So everything is completely explicit, modulo working out the formulas. And a hyperbolic surface is something that locally looks like this. So how do you create something that locally looks like this? You just take bits of it and you glue them together into a surface. So one of the ways to do that is the following thing. So here's the hyperbolic plane again. One thing I can draw in the hyperbolic plane that I cannot draw in the Euclidean plane is a right-angled hexagon. So what do? I draw 6 geodesics that all meet each other at right angles. Also, because the metric is locally a rescaling of the Euclidean metric, the angles you see in the picture are the honest angles, are the angles for the hyperbolic metric as well. 1, 2, 3, 4. Oh. Okay. Bam. All right. So here I've drawn 6 geodesics. They are all supposed to meet each other at right angles. So there's a little continuity argument to say that this actually exists, but it does. And the right angle hexagon is just this thing. Beg your pardon. And actually the continuity argument tells you what? It tells you more than that. It tells you that if I give you 3 non-consecutive lengths, so here, for instance, A, B, and C, there is a unique one of these figures. There's a unique right-angled hexagon up to moving it around in the hyperbolic plane by an isometry. So this is a trigonometry fact. For every A, B, C positive, there is a unique right-angled hexagon. And these I can use for building blocks for surfaces. So what can I do is I take 2 of my hexagons. I'm going to draw them floating in space. I'm going to forget about the hyperbolic plane. So here's 2 of them. Well, if they have the same, so given A, B, and C, given 3 non-consecutive, 3 lengths for 3 non-consecutive sides, there's a unique one. So if I take 2 copies of that thing, it's the same thing. It's the same metric object. It's the same hyperbolic surface with boundary. And what can I do? I can glue the sides that I have not marked by a length together into pairs, because since A, B, and C determine my hexagon, that means that these 3 other sides need to be the same length as well. So I can glue them. So I glue that to that, this one to the side over here, and this one to that side over there. So that gives me the following figure. So I haven't done anything with the sides of length A, B, and C. So that gives me something that looks a bit like this, a hyperbolic pair of paths. And the original right-angled hexagon sits on it like this. mean, this is the copy on the front, and the complement is the copy on the back. Here's one right-angled hexagon, and the side lengths will be length 2a, 2b. I see that I've labeled them differently on the left, but okay. The side lengths will be 2a, 2b, and 2c. And with the same geometry fact here as this one, there's also a unique hyperbolic metric given the boundary lengths. So actually, these three real numbers, they determine the hyperbolic metric in the middle here. So fact 1, fact 2. And there is a unique for every ABC positive. There is a unique hyperbolic pair of pants. Pair of pants with boundary components. Oops. Of length ABC respectively. And that's useful because now I can use these pairs of pants as building blocks. So what can I do? I can, for instance, if I take two of them, oops, so that's really. If I take two of them with the same triple boundary lengths, so this one is length A, this one 2, this one is length B, that one 2, this one is length C, and that one 2. Then I can do the same thing. I can glue the pairs together, and that gets me a surface with a hyperbolic metric on it. So that gets me something like this, where the original curves from the pairs of pants, they glue into curves like this on the surface. Okay, and now so this whole figure is supposed to convince you, even if I've skipped over all the details, is supposed to convince you that with these right-angled hexagons I can build pants, and with these pants I can build lots of hyperbolic surfaces. So this gives you lots of hyperbolic surfaces because I mean they're built out a piece of hyperbolic plane. So this is a surface with a metric on it, and it's locally just a metric of hyperbolic plane. And then just counting parameters. So per pair of pants, I have 3 parameters for the boundary lengths. And then in the gluing, I also have a choice. So I want to glue, so these two curves of length A here, for instance, these two. If I glue them together, I have a choice in the sense that, of course, I want to glue them with an isometry so that the metric glues up nicely. But I need to tell you where one point goes. So for instance, if I tell you that this point goes here, then that determines the gluing, because then a point at distance, that yellow is not very visible, sorry. Point at distance X here needs to glue to a point at distance X there as well. So given the image of a point, I know where it goes, but I have one extra degree of freedom. So what I'm trying to tell you with these pictures is that if I give you just a surface, a picture of a surface like this one here, and I give you 2 parameters per curve in the decomposition into pair of pants, I give you a hyperbolic metric. And then topology argument tells you that I see that my co-author joined the room as well. The topology argument tells you that tells you that this gives, for a surface of closed surface of genus G, gives you 6G minus 6 parameters. So 6G minus 6 parameters. So so what I'm really saying here is that you get a 6G minus 6 dimensional space of hyperbolic metrics. So 6G minus 6 dimensional space of hyperbolic metrics. Sorry. All right. Okay, which is usually called moduli space. Sorry, G, I said G, but I haven't defined it. So G here is the genus of the surface, the number of holes. So this is called mg. This notation that I'm going to use the whole time. So the analog of these packing problems is, well, I haven't given you the analogs of the shortest lattice vector and the kissing number yet, for instance, but the analogous problem is going to be an optimization problem over this set, because in fact this set, this moduli space, it contains all hyperbolic metrics. So you can construct all hyperbolic surfaces of genus G like this. And the analogs of these packing problems are going to be questions: what is the surface in this set MG with the largest, whatever the shortest lattice vector is going to be, and these kind of things. Any questions so far? Okay, so if not, then I wanted to talk about what are these analogs to the Euclidean packing problems. What's the analog of the shortest lattice vector, for instance? So the geometric invariance. So I've sort of alluded to this already, but the shortest lattice vector, you can think of this as a problem on the space of tori. So associated to a torus, to a lattice in Rn, there's an n-dimensional flat torus, just the quotient. So if lambda is a lattice, then you get a torus, flat torus, Rn mod lambda. And what is the shortest lattice vector? Well, for instance, okay, if I draw the hexagonal lattice again, so then what is the torus? Or no, let me just draw the square lattice. So here's a square lattice, right? If I take the quotient, then this square here is a fundamental domain, and the shortest lattice vector is just going to be these guys, and this is the shortest lattice vector, right? And in the quotient, what is this? If I take the quotient here, then these two red lattice vectors, they glue up to loops that look a bit like this. So the shortest lattice vector is nothing else than the length of the shortest lattice vector is nothing else than the length of the shortest loop on the torus. So this is usually called the systole. So systole is the length of the shortest closed geodesic. Shortest closed geodesic, which is the same as the shortest lattice vector in the lattice. And the kissing number is what? The kissing number is just the number of directions in which you have a shortest lattice vector, except you multiply by 2 because you let me just draw it. So it's the number of directions in which you have a shortest lattice vector. So that, I mean, note that the two vectors that I've just added give me the same curves, but with the opposite orientation. So the kissing number for a torus is just the number of is just the number of systoles counted with possible orientations. Okay, and the upshot is that the quantities, the systole and the number of systoles, these are quantities that are perfectly well defined for hyperbolic surfaces as well. If I have a hyperbolic surface, maybe it looks something like this. Then the systole will roughly be the length of the curve that goes around this this tube here. And the number of systoles is just the number of curves that realize it. So these questions can be asked for hyperbolic surfaces, and they have been asked by many different people. So those are the first two invariants that I want to look at. Fix the genus of the surface, look at the space, the moduli space of all possible hyperbolic metrics. What is the maximal possible systole? And likewise, the same thing, what is the maximum possible number of systoles? So it turns out that both these maxima are finite. And the question is just what they are. Now, Now there are a couple more problems that are analogs to these problems in the hyperbolic setting. So we've already seen the dual torus appear it appears in the Poisson summation formula. You can also ask for the shortest lattice vector in the dual torus. So question not so that let's say shortest lattice vector in Rn mod dual torus. Of course, in the Euclidean case, this doesn't give you a new optimization problem because the dual torus is a torus as well. It's also a flat torus, so you're optimizing the same quantity as before. But what is this really? We've seen that the dual torus in this proof of the Poisson summation formula, the vectors in the dual torus correspond to eigenfunctions of the Laplacian on the torus, and that you can do for a hyperbolic surface as well. You can look at the Laplacian, and you can look at the smallest non-zero eigenvalue, which is the analog of this, which for a hyperbolic surface is a different problem. So this equivalence between the two problems goes away. So let me just give a tiny bit of context. So this is smallest non-zero eigenvalue. Non-zero eigenvalue of the Laplacian on Rn. Let me see. No, that doesn't fit. All right, so let me make some space. Where does this go? Okay, are there any questions while I wipe the board?
I am not sure if I understood the last thing about the dual lattice being the smallest eigenvalue.
Yes. So this is something I mumbled during the proof of the Poisson summation formula. So at some point I said, let me go back to that should still be there. Yes. Well, at some point I said here in this decomposition. So in this trick I used that big F here is really a function on the circle. Mm-hmm. And then I said, well, I mean, under the right assumptions is an L2 function on the circle. And I know that L2 I can decompose as eigenfunctions for the Laplacian. Okay. And the eigenvalues are exactly the eigenvalues. The roots of the eigenvalues are what you see here, right? 2 pi k is the root of the eigenvalue.
Okay.
If I apply the Laplacian twice, then 4 pi squared times k squared comes out. And this is a general phenomenon because what is k here? In this simple case, k is a vector in the dual lattice. It just so happens that the dual lattice to z is also z. Okay. But in general, the eigenfunctions for the Laplacian for the torus are completely explicit. They're these exponentials, and their eigenvalues are just lengths of vectors in the dual lattice.
Okay.
Does this answer the question? Was this the?
So in the dual. Okay. So here the dual lattice is also z, mm-hmm. And it's exactly the k that we found in the exponential. This, if I understand right.
Yeah. Exactly. Yes. Okay, but, yes.
It means that these are all the eigenvalues, no?
This is the complete set of eigenfunctions.
Not only the smallest.
This is the complete set of eigenvalues.
Complete set.
Exactly. The dual lattice, I mean, is up to normalization. It's a set of gives you the set of the lengths of the vectors in the dual lattice up to multiplying by a constant and taking a square gives you the list of eigenvalues.
Okay.
And
but later you say that it's the smallest. Actually, this is the point that.
So if you now ask, so you can ask the shortest lattice vector, you can ask it for the dual lattice as well. And that comes down to asking for what? That comes down to asking for the smallest non-zero eigenvalue.
Okay.
Yeah, that answers the question.
Thank you.
All right. Okay. Anything else? Any other questions? So, okay. So if not, then I wanted to just briefly, I see that there's less than 10 minutes left. So I just wanted to briefly develop what the analog is of that. So again, for the torus, looking for the smallest eigenvalue of the Laplacian comes down to looking for the shortest lattice vector again. So the optimization problem is the same, but for hyperbolic surfaces, it splits into two problems. So let me write that out. So first of all, what is the Laplacian in the hyperbolic case? So the Laplacian, it's always the same thing. It's minus divergence composed with gradient. This is what you do in Rn. And on the Riemannian manifold, divergence and gradient are always defined, so you can always do this. And in the hyperbolic plane, this just comes down to the following operator. It's minus y squared times ddx squared plus ddy squared. So it's the usual Euclidean Laplacian, but there's an extra factor, y squared. And just like in the Euclidean case, this descends to an operator on functions on a hyperbolic surface as well. And just like in the Euclidean case, you have a spectral theorem. L2 of the surface decomposes into, it has the eigenfunctions of this thing form an orthonormal basis for L2 of the surface. So let me write that down. This is the spectral theorem. So theorem is that this is a positive operator. So the delta as a, so let me be a bit more precise. So X here is a closed and connected hyperbolic surface. Closed means compact and no boundary. So you think of these surfaces of genus G from before. A hyperbolic surface. And so then delta, this Laplacian, it acts on, say, smooth functions on my surface. And it has a discrete set of positive eigenvalues. The first one is 0, because constant functions are annihilated by this thing. The gradient already annihilates constant functions. It has a discrete spectrum of eigenvalues, 0, which is lambda 0. And then I'm assuming, this is why I'm making a point of writing connected. If it's connected, then the first one, let me write it, lambda 1 of x. The next one is strictly positive. And then number 2 might be equal, and then it continues. And it's discrete, so it flies off to infinity, the size of the eigenvalue. So this is really, this is true for the torus as well, but this is true for hyperbolic surfaces. And you can ask, so this eigenvalue, this lambda 1, it also has geometric meaning. For instance, it's a measure of connectedness. The larger this lambda 1, the more connected your surface is. For instance, if you put a Brownian motion on a hyperbolic surface, then if lambda 1 is large, then it equidistributes quicker than if lambda 1 is small. But it appears in all sorts of problems. So it's interesting how large it can be on the set of all hyperbolic surfaces. So and likewise, so that's the analog of, say, the shortest lattice vector in the dual lattice. And there's also an analog of the Kissing number for on the spectral side, which is just the multiplicity of this eigenvalue. So M1x, M1x equals the multiplicity of x. lambda 1x. All right. So our question, our basic question is just the analog of the packing problems, is just how large can these quantities be? What is the maximum possible systole? What is the maximum possible kissing number? So the number of systoles. What is the maximum spectral gap? What is the maximum multiplicity? Then I haven't said anything about small eigenvalues, and I'm going to skip that for now. But there's another interesting integral quality, which is the number of small eigenvalues. So first of all, just to convince you, there's lots of work on this. I certainly don't have time to do an overview of what is known. So here's a very incomplete list of people who've worked on this. Here are two nice pictures of hyperbolic surfaces, of which we know that there are optimizers for some of these problems. So here on the left, I've made a cartoon of the Boltzmann surface. It's a surface you can get from gluing certain polygons together that come out of the hyperbolic plane. I've drawn the combinatorics of the gluing pattern. The Klein quartic. So this becomes a surface of genus 2. And we know it optimizes certain problems. And then there's the Klein quartic, which is a surface of genus 3. There's the gluing of the sides of this polygon that I have not drawn in. And we also know that optimize, but actually we know very few optimizers. So here's for global optimizers, here's a complete list of optimizers. So you see that in the table, it already says conjecture a bunch of times. The Boltzmann surface optimizes the systole and the kissing number in genus 2, probably also lambda 1 in the multiplicity. And in genus 3, the only one that we know is the Klein quartic, which is an earlier paper together with Max. And in higher genus, we only have local optimizers that we know. So we know very little, except for these small eigenvalues we have about, but I haven't told you what they are. So this is the new work in the last 2-3 minutes. So what we've done with Max is we've adapted this Cohen-Elkies theorem, this thing that came out of the Poisson summation formula. So there's a hyperbolic analog for the Poisson summation formula, which is called the Selberg trace formula, which you prove in a very similar way, except that the computation is a lot more difficult. And so these are the bounds we get. So the nice thing is that, sort of similar to the Poisson summation formula, the Cohen-Elkies approach, we improve the previously known bounds in most cases. So there are a couple of cases, especially for lambda 1, there are a couple of cases where there's a recent paper actually by mathematical physicists who in genus 2 and 3 do better than us. This is Kravchuk, Mazak, and Pal. So the blue line is always us. The green line is always the number of the best known surfaces. So here in green, we have the best known surfaces for the systole in the first picture, for instance. The blue is the bound we get out of linear programming, and the red is what was previously known. Maybe the last slide that I'll show you, and then I'll stop. So actually, we don't only get better bounds in low genus, which may mostly come out of rigorous computer proofs, but we also get new asymptotes for all these quantities. So we also have asymptotic upper bounds for all the quantities that we were interested in. And I think this is a good point to stop. Thank you very much for your attention.
Thank you very much.
Thank you very much, Bram, for the talk. So are there further questions from the public?
Maybe I can. First of all, thank you very much for the very pedagogical and clear talk. And sorry for the interruption, because I think I interrupted many times already.
No, thanks for the...
Actually, I hope at some point you mentioned at the beginning, I thought the kissing number for the lattice with the circle is 5. then you say that it's the number of directions. So I just want to make sure. Maybe
it's 6. So you see, I mean, you look, for instance, at this sphere, this disk here, and you see
but
that.
When the lattice is square, it's 4.
When the lattice is square, it's 4. Yeah.
Okay.
Yeah. This is the best one. This is the unique optimizer. In dimension 2.
Okay. So maybe I can ask also about the hyperbolic context, because here to find the theorem that you showed about to have the linear conditions on the function.
Mm-hmm.
In order, so the main theorem in I don't remember this one.
This is the hyperbolic version. I didn't get to this. I planned more slides than there was time. But this is type. It's really an analog in the sense that in the end, it reduces the geometric problem to a calculus problem in a sense. So here it says I mean the conditions are of course different because they come from hyperbolic geometry and not Euclidean geometry. But here I put down the one for the systole.
Okay.
As you can see from the slide, I was optimistic and thought I was going to prove it too, but
and the proof goes along the line of the first. It means by contradiction of some.
It's the same kind of thing, except that it's the same kind of thing, except that the Poisson summation formula is replaced by the Selberg trace formula, which is this one. This is really, I mean, it looks more complicated, but this is really the analog of the Poisson summation formula in the hyperbolic setting.
Okay.
I don't know if we can connect this to because Selberg formula can appear to in context of automorphic functions also. I don't know if there is some connection between what you do and automorphic functions and.
No, absolutely. So an automorphic function. So an automorphic function is a function that is invariant under a Fuchsian group acting on the upper half plane, right?
Yes.
And that's the same as a function on the quotient for the same reason as in the Poisson summation formula. And the quotient is a hyperbolic surface. So the upper half plane, comes with this hyperbolic metric, and you have this Fuchsian group acting on it. Let's call it gamma. This preserves the metric. So the metric descends, and this will be a hyperbolic metric. So this is the same Selberg trace formula as from the theory of automorphic functions. It's the same thing. Okay.
And you have exactly the development according to the eigenfunctions of the Laplacian and in some sense.
These, I mean, people working in automorphic forms, I think they usually call these mass forms. I mean, well, in the context of very specific Fuchsian group, but yes, short answer is yes.
Okay, thank you very much. Okay, that's it for me. Maybe there's another one.
Okay, are there any further questions?
Is it still recording?
Guess so, yes. Okay, so if there are no other questions, I would thank again Bram for the talk, and
thanks for having me.
Thank you very much, and see you in 2 weeks for the next talk in this geometry and general relativity session.
Cool.
Thank you very much,
and well, see you soon, I guess.
See you
soon.
Yeah.
Thank you again, and have a good day.
Thanks for coming. Nice meeting you.
Thank you, Bram. See you.
Yes. It's the same. It's my pleasure.